All right, so hello everyone. So welcome back to the RL Theory seminars again. And as always, like during these talks, like feel free to ask any questions, just unmute yourself and you can ask during the talk. And if you want to ask in the chat, you can do that as well. And I can just unmute myself and ask the question for you. In terms of Q&A stuff, like there's also going to be like a longer Q&A at the end of the talk. So the talk will be about 50 minutes. And then after that, there'll be like an extended Q&A where you can ask like your longer questions. So maybe if you have longer questions, just hold out till the end of the talk. And today, the co-host will be Gergely here, and he'll be also stimulating the speaker with some technical questions throughout the talk. And yeah, and our speaker today will be Audrey Huang. And Audrey is a third-year PhD student, candidate in the computer science department at UIUC, and she's advised by Nan Jiang. And her research focuses on theory and design of reinforcement learning algorithms. And prior to UIUC, she obtained a master's at CMU's machine learning department and a bachelor's in the computer science department from Caltech. So without further ado, Audrey, feel free to start.
Yeah, thanks for the intro. I think I probably wrote the most generic bio ever, but thanks anyway. Yeah, the title of our paper is Reinforcement Learning in Low-Rank MDPs with Density Features, and this work is co-authored with my lab mate, Jinling, who's in the audience, I think, as well as Nan, who's also in the audience. So, okay. Let me first explain what the density features are in low-rank MDPs. So as we're all probably familiar with, low-rank MDPs are the structural assumption where the transitions admit a low-dimensional decomposition into these two matrices of rank D. So the left matrix in orange is denoted phi, and the right matrix denoted mu. And most previous works have focused on the setting where phi is known or learned because it can be used for linear function approximation of the value functions in model-free RL, which is relatively well understood. But our work considers known or learned mu, which we use for linear function approximation of the occupancies d pi. And since occupancies are density functions, for this reason, we'll refer to mu as the density features. Very quickly, everything in this presentation is in the finite horizon MDP setting. So there are h total time steps, which I'll also refer to as levels. And for each time step, let's say we've observed the state x h minus 1. The agent will take an action according to the policy pi h minus 1, and then observe the reward and the next state according to the corresponding dynamics at h minus 1. So in this finite horizon MDP, the occupancy dh pi of a policy pi represents its distribution over states at time h, which is visualized on the right. The occupancy obeys the recursive Bellman flow equation, meaning that the relationship between occupancies at adjacent time steps have to follow the dynamics of the underlying MDP, and specifically the occupancy at time h is equal to the occupancy at time h minus 1, pushed through the probabilistic policy and transition operators. So for short, we'll frequently denote the Bellman flow operator by this bold p h minus 1 pi. And in low-rank MDPs, you can show that the dh pi is a linear function of the density features mu, meaning that it can be expressed as the inner product between mu and some d-dimensional parameter theta. To illustrate that in this example, we have d equals to 2, and mu consists of these two simplex features in blue and pink, meaning that it's just a basis of two representative distributions. And any other occupancy will be a convex combination of these two basis distributions as expressed by theta, and then this theta for dh pi is shown here. So why occupancies for RL? The first reason is that they're a very natural function to guide exploration with because they essentially tell us which states are important to collect data from. And the second reason is that for the learning part of RL itself, the occupancies directly determine the expected return of a policy by taking the dot product with the reward function, which is the expected return we want to maximize. So based on this intuition, in this paper, the question we answer is whether sample efficient offline and online RL with density features is possible in low-rank MDPs. And we have several motivations. The first one is that we can get plug-in solutions for convex RL, which value function learning is often incompatible with. So in convex RL, we want to maximize or minimize Lipschitz convex functions of the occupancy d pi. And for example, the expected return is a special case where you have a linear function of d pi in terms of your reward r. And this is flexible enough to include other well-known functions such as imitation learning, where we want to minimize the L1 distance between our occupancy d pi and the occupancy of an expert policy pi e. And this also includes something like max entropy exploration. The second motivation is just to fill in a gap in the literature where most works before ours have focused on learning through the phi features to go through value-based RL methods, and ours is the first to go through the density features. And it becomes clear in the representation learning setting where phi is unknown that exploration with the value features can be difficult. For example, MOFL, which is the second row from the bottom, requires some reachability assumptions to make this work. So this brings me to the third motivation, where hopefully with the density features and occupancies, we can explore more efficiently and obtain better guarantees in the representation learning setting. And lastly, this also provides some theoretical foundation for RL on top of unsupervised learning oracles and generative modeling, which is what we later use to model the occupancies, and which is frequently used in empirical RL. So let me first present the main result for online RL. The assumptions we make are the following. So
Can I ask a quick question?
Yeah.
This is probably quite naive, but can you just, if you like going back here, can you just maybe explain a little more of why here we're kind of assuming that we now have mu as opposed to phi before, like knowing getting features seemed like a very natural assumption. Like what's going on in this setting? I'm a little confused.
What do you mean by getting features is a very natural? Do you mean like getting phi is natural and mu is not, or?
Yeah, that's what I mean. Like I understand the features like from this table here that in these prior works, right, you're given like this feature like map and you use that for learning like some unknown parameter mu. But here are you saying that we're given the unknown parameter mu and we're trying to
so yeah, it's not really that phi is used for the unknown parameter mu necessarily. So phi is can be used to represent the value functions q pi without using mu at all. Assuming that mu is known is just like sort of an analogous assumption, but for the other matrix in this decomposition, where we can use them to model another type of function, which is the occupancies. Does that answer your question, or?
No? Oh, right. It's modeling the next state part.
Yeah.
Okay. Is there some? Yeah. Okay. That's fine.
So I had another question regarding like not necessarily the motivation, but how an approach in this setting would work. I'm sure that this is going to be answered in time, but I still want to have some confusion out of the way before that comes. So if you're optimizing in the space of occupancies, then sure enough, you can phrase all of these optimization problems, as you stated, like maximum entropy exploration, maximizing rewards and stuff. But what is the solution going to be that you get? Is it going to be state occupancy, but how do you extract a policy from that? Or
yeah,
I guess
so
this is like the high level question
that is a good question, and I was going to answer it in one slide.
Okay.
so maybe let me try to do that,
right,
and then go back to your question.
All right. Okay, perfect. So then please.
Okay, maybe it wasn't. Okay, it was almost one slide. Okay, yeah, it actually was one slide. So
right.
Yeah, anyway, let me just clarify our assumptions first. So we have a finite policy class, and let's say we know the density feature mu. So this is analogous to in linear MDPs where you know phi. And the outline for our online RL method is the following. So first, we have to estimate the occupancies of all policies in a reward-free manner. And these estimates should be close to the true occupancies in the L1 norm. And afterwards, when we're given a reward function R, we can just output the policy pi hat that maximizes the estimated expected return denoted j hat r pi, which is calculated using the estimated occupancies. So I think this answers your question where, like, let's say in value functions, there's like a straightforward way to get policies where you learn q star, but you don't have something analogous for the occupancies. So here we're aiming for something sample efficient where for doing this procedure, but it's not computationally efficient because you have to estimate all of these occupancies basically.
Oh, there's also some slides subtlety here that may be slightly confusing is like, I think you're making I think dpi throughout this work is state occupancy. So technically speaking, it's not a direct dot product with R, right? But you can always expand a state occupancy into state action by just combining with the policy. Yeah, otherwise it's straightforward.
Okay.
Right, so but this suggests that whatever you do is going to be limited to finite policy classes?
Yeah, for now it is, unless there's some way to generalize between policies to do some kind of union bound easily.
I see. Okay.
No, I think so we'll get our result will just have a log pi dependence as usual. I think if you want, like, do a covering number or something like that, it should be straightforward. I think the real issue is computational, which we're not addressing here, but it's ongoing work.
All right. Okay. I think I understand the plan, at least on a high level.
Yeah. So let me just flash the guarantee we get for online RL, which is of this form. So with high probability, we can show that pi hat has expected return, which is JR pi hat. That's within epsilon of the maximum possible expected return. And the sample complexity is polynomial in the rank of your MDP D, as well as your actions A, the horizon H, and then this log of the cardinality of pi dependence and epsilon to the -2. So in this outline, once we have the reward-free occupancy estimation guarantee, the policy learning part is pretty much straightforward. And so the meat of the problem is in how we can estimate the occupancies uniformly well in an online manner. There are two components for doing this. So we need sample efficient methods for estimating occupancies DH pi from data with sufficient coverage, as well as collecting data that will sufficiently cover the occupancies. This also hints at one of the fundamental challenges of our problem, which is this sort of bidirectional relationship between these two components, where we need exploratory data to estimate the occupancies, but in order to collect this data in a sample efficient manner, we'll need information about the occupancies themselves. And if we don't interleave these two components well or analyze the resulting algorithm correctly, it'll be very easy for the error to exponentiate because of this cycle. And I'll go more into detail about that later. So let me get started by talking about the first component, which is how we can estimate the occupancies at all time steps from data for a given policy pi. So we know that DH pi obeys this Bellman flow equation and also linear function of mu. And there's an analogous problem that's been well studied for value functions, which obey the Bellman equation and are linear in phi in low-rank MDPs. And basically from the linear MDP literature, we know that fitted Q iteration, or FQI, can estimate Q pi with a sample complexity that's polynomial in the terms that we care about. So FQI recursively approximates the Bellman operator from samples. And our idea is to do something similar and recursively estimate DH pi from DH minus 1 pi by using regression to approximate the Bellman flow operator. So before introducing what this regression objective will look like, let me first introduce like the dataset notation. So we're given a tuple dataset dcal h minus 1 that consists of xa x prime tuples, and x is drawn from the data distribution ddh minus 1. A is drawn from this behavior policy pi d h minus 1, which we assume is known. And then we observe x prime from the transitions, and we denote the marginal distribution of these next states as dd dagger h minus 1. So because we're estimating a distribution from another distribution, it turns out that we can't directly use dh minus 1 pi in regression. And instead we have to use its density ratio, denoted wh minus 1 pi here, which is the fraction of the occupancy over the data distribution at level h minus 1, assuming that this data distribution is known. And we'll use regression over the data set to fit a function wh onto this boxed expression, which I'll refer to as the regression target, which is composed of the density ratio times an importance weight that deals with the mismatch between pi and the behavior policy used to collect data. So for a general regression of the form shown here, where you try to fit a function f to predict y from x, the minimizer f star at x is the conditional expectation of the target y given x. So in our objective, the target involves xa, and the minimizer wh star at x prime is the conditional expectation of the target at xa, given the next state x prime. When this is written out, this is a ratio where the numerator involves the Bellman operator applied to the pointwise multiplication of the data distribution, and the density ratio at level h minus 1 divided by the marginal distribution at x prime. And this plays out to be another density ratio, which is equal to something having the occupancy at time h in the numerator, which is the occupancy we want to learn. So because we have to output a density, we will just extract dh pi from the numerator by taking the pointwise multiplication between wh star and the marginal in its denominator. And lastly, I want to point out that this objective alludes to a kind of coverage condition we need to make regression work, which is that in order for this density ratio to be well defined, we're going to need dh pi to be bounded on ddh for all levels, since we'll call this function recursively. That brings me back to the two parts of the online occupancy estimation problem. And at this point, we now have some confidence that we can estimate the occupancies using a regression type method. So the next question I want to tackle is how we can collect data that sufficiently covers these occupancies in the first place. And let's bring back the square laws objective we proposed for estimating the occupancies just now. So this objective requires two ratios to be bounded. And the first one is the density ratio between the occupancy of pi and the data distribution of h minus 1, which we actually need to be bounded for all pi since we're estimating the occupancies of all policies. So to formalize this coverage requirement, I'll first define this concentrability coefficient shown below. Given a policy class pi and distribution d, the coefficient, the concentrability coefficient at level h is denoted as cc sub h of d, and it's just the smallest constant, small c, that bounds the density ratio between the occupancy of any policy in big pi and the input distribution d. So translating this to our regression problem, what we need for regression is that ddh minus 1 has a concentrability coefficient upper bounded by some finite constant big C. And to visualize this requirement, the graph on the right shows the occupancies of all policies at level h minus 1 in different colors. And what we need is to design an exploratory policy that when we roll it into this level h minus 1, the induced data distribution shown in the dashed line satisfies this coverage requirement. The other ratio we need to be bounded is this policy ratio between pi and the behavior policy pi d, which we also need to hold for all pi. And it's straightforward to just set this to this behavior policy to take uniform actions to satisfy the coverage requirement. And so in the graph on the right, I'm now showing all the occupancies pushed to level h. And if we already have coverage at level h minus 1, taking uniform actions between level h minus 1 and h guarantees that we still have coverage at level h, but with a diluted concentrability constant of Ca. And I also mentioned this to just point out that the minimizing WH star that I discussed previously is also well defined with magnitude bounded on Ca as a result. So the hard part of the exploratory data collection is in designing this exploratory policy that will roll into level h minus 1. And for example, a naive approach where we uniformly deploy all policies in the policy set will work, but you'll get a concentrability coefficient, which later appears in our sample complexity and reflects how diluted the data is then equal to the cardinality of the policy class, which can be exponentially large. So to overcome this, we need to take some kind of more intelligent approach where we exploit the linear structure of the occupancies, specifically that they're all linear in the same d-dimensional features, which indicates we might be able to get some concentrability coefficient that's polynomial in D. It turns out that we only need D policies to explore each level, and this comes from something called the barycentric spanner. So in low-rank MDPs, in any level H, there exists a set of D policies called the barycentric spanner, shown in pink, and that I've denoted pi h1 through pi hd, such that for any policy pi, its occupancy is upper bounded by the sum of the occupancies belonging to the policies in the spanner. A brief proof sketch is that each d pi lives in a d-dimensional subspace due to linearity in mu, so we can write it as a linear combination of some d-dimensional basis But we want to build this basis from the set of all possible occupancies. So we'll do it in a volume maximizing manner, which corresponds to the policy selected for the spanner. And this basis represents some principal directions of variation for the occupancies. So from this, you can see that you can show that any d pi is a linear combination of these d basis occupancies with coefficients between -1 and +1 per the equation here, which directly leads to the lemma statement. Okay, so going back to the lemma and its implications for exploration, with a small rearrangement, you can show that the occupancy of any policy is bounded on the uniform mixture of the occupancies of the spanner policies with a coefficient of d. And the direct implication is that the uniform mixture of policies in the spanner has a concentrability coefficient of at most d, which means we can collect a tuple data set in the following manner. So let pi span h-1 be the policies in the spanner computed to explore h-1. We'll roll the uniform mixture of the spanner into observed state x h-1, which the spanner lemma guarantees has concentrability coefficient of rank d. Afterwards, we'll just take uniform actions and observe the next state xh, which has a diluted concentrability coefficient of dA. And then since this data set satisfies the coverage requirements that we need, we can now estimate the occupancies for all policies using the regression method discussed previously. And then now notice that we actually have approximations of the occupancies at level h, so we can repeat this process by computing their barycentric spanner, pi span h, and roll it into level h to shrink the concentrability coefficient back to d. So this means we can go back to step 1 and repeat the process of occupancy estimation for dh plus 1 pi at the next level. So this sequence of estimation and exploration makes up the general framework for our online occupancy estimation algorithm, which just does exactly the procedure I just mentioned from time steps h equals 1 through big H. Okay, so this seems great, but when we put this algorithm together with the estimated d hat, it turns out that some of our original reasoning will break down pretty significantly. So the main issue is that when the barycentric spanner is calculated from these estimated occupancies, it only guarantees that d hat is bounded on the average of the d hats in the spanner. So if you recall our proposed method, the population version at least, for recursively estimating the occupancies, we need this dh pi ddh density ratio to be bounded. And the problem is that the barycentric spanner involving these estimated d hats implies nothing about the boundedness of this density ratio involving the true d pi in the numerator, or even d hat pi in the numerator. And in general, this quantity may not be bounded at all. So to visualize this in the graph on the left, the distribution induced by the spanner calculated from d hat is shown in the dashed line. So you can see that there's portions of the occupancies that just aren't covered by the data. And for these portions, there's no hope to estimate them well at all. So the question we have to ask is how we can resolve this issue, both conceptually and numerically. Yeah, so one simple solution is to just clip the density ratio to have magnitude at most c, which is an input parameter, which is shown in the green box on the right. And for our algorithm, setting c to be the rank d makes sense because it's the concentrability coefficient of the true spanner. And in terms of the analysis, which I'll discuss shortly, the idea is that the clipping will just add a bias term, and if the spanner is near fully exploratory, then the occupancies will be almost fully covered, and this bias should be small. Before moving on to the analysis, I want to quickly introduce the finite sample version of the algorithm called fork, or fitted occupancy iteration with clipping. So the function call is shown on the left in green, but it takes an input dataset dcal h-1, the previous level estimate d hat h-1 pi, and this clipping parameter c. And it first estimates the occupancy ratio by minimizing the empirical squared loss with the regression target w tilde. That clips the ratio of d hat h-1 pi over an estimate of the data distribution d hat d h-1 and multiplies it by the policy ratio. So previously I've assumed that ddh-1 is known, but we can just use standard maximum likelihood estimation guarantees to get an estimate for this data distribution. And the function class wcal_h is linear over linear with bounded norm. So the numerator is a linear function of mu, and so is the denominator. And we can control the complexity of this class using the rank D. And the typical supervised learning style analysis should give us something that we consider to be sample efficient. So finally, we'll just extract the occupancy estimate d hat h pi by taking the element-wise product between w hat and dd dagger h minus 1 hat, which is the next estimated next state distribution in the data, which we can also get from Emily. Yeah, so before moving on, I just want to address a small detail in case it's bothering anyone, that after the element-wise multiplication step in fork, the resulting d hat pi may not be a linear function in mu, but we need functions that are linear to compute the barycentric spanner. In our paper, we just deal with this by outputting the closest linear approximation to the original estimate, which only increases the error by a factor of 2. So in the proof, which I'll talk about next, I'll just treat the d hat as linear for ease of analysis.
I have a quick question.
Yeah.
It's about the previous slide, but you had like this picture, you were saying something about there not being proper coverage, and this is why. What was going on in this picture? Like can you explain this intuition again here?
Yeah, so here, I don't know if my cursor, can you see my cursor?
Yeah, I can see it.
Oh, okay. Okay, let me go back one slide. The spanner here is calculated from estimated occupancies.
Mm-hmm.
So the barycentric spanner only states that the estimated occupancy of a policy is bounded on some mixture of the estimated occupancies of other policies.
Mm-hmm.
So when we roll this distribution, this spanner into level h minus 1, basically what we get is only the induced distribution in the dashed line is only going to have approximate coverage of the true occupancies, which are shown in color.
Mm-hmm.
So if you had something like d hat h pi being equal to d h pi, this dashed line would cover everything properly. But because you're using an estimate, you only get a coverage of the estimated occupancies, which doesn't imply coverage of the true occupancies. Does that make sense?
Yeah, I see. And you can't account for the error there, or it's like the error will propagate poorly or something in this setting, in this case, if you just did this way of analyzing it?
Yeah, I mean, to begin with, like, you have to use this density ratio in your regression. So if this term is not bounded, then you can't really get anything out anyway. So
yeah, you can even get infinities in your regression argument, right? So you first have to do something algorithmically before even getting to analysis.
Yeah, thank you.
Thanks for your question.
Right. So I'm wondering about, I suppose a similar question is that you said that you're going to be estimating the spanner from the occupancies that you estimate. So there's this kind of like a vicious cycle thing going on in there. So I'm just really trying to like wrap my brain around this, because you see that this is like a quite complicated procedure at the end of the day. So I guess like one thing that is probably worth highlighting is that the W star that you learn here, so these are like separate W's for the separate pi's, right?
Right, yeah.
And you're enforcing this linear over linear structure on this. And as a result, you're gonna be getting a parameter theta, well, sort of ish, for each d pi. Is that right?
Yeah.
Right, and then you just essentially need to find a spanner for these thetas that you find. So you get like pi many d-dimensional vectors, and you need to find a spanner for this set. Am I reading this correctly?
Yes.
Yeah, that's correct.
Okay.
Yeah.
Right, and this is why I need to enforce this linear over linear structure.
Right.
Otherwise,
you
get total mess.
Right, that's correct.
Right. Okay. Got it.
Yeah. Okay. So.
Yeah, I guess I was just asking this because this was like not really explicitly written in this algorithm description that the spanner actually comes from the result of this.
Yeah. I could have made that more clear for sure.
Right, okay.
So the spanner is calculated from d hat h pi for all pi.
Also, part of this is because the result is our results so far is purely statistical, right? So you can just say, well, for anything like that, it just exists, so we can just find it. But I think, the way you put it, like computing the spanner from the theta parameters, is definitely a more concrete way of visualizing what happens.
Right. Yeah. Okay. Nice. Got it.
Okay, so let me start discussing how we can bound the estimation error between the d hat h pi output by this algorithm, which we call force, and the true occupancy. So the typical strategy for bounding the error in this type of regression algorithm is to inductively bound d hat h pi, the error between d hat h pi and dh pi, using the error at the previous time step. But the issue here is that we will get an exponential error blowup, which is O of d to the h, where the error at time h is upper bounded by 1 plus d times the error at level h minus 1, and so on. And on a high level, this is because we add on estimation error every time we use d hat h minus 1 in our algorithm. So we get d times this quantity for each occupancy in the spanner, which is because the quality of estimation error will affect the quality of the spanner's coverage, as was just alluded to. And we also get 1x the estimation error from using d hat as a target regression. So we also see that the quality of coverage is affecting the estimation error as well. And this is exactly the bidirectional relationship between occupancy estimation and exploration that makes the analysis here difficult. So from this, we can see that the underlying reason for the exponentiation is this two-way relationship between the two sources of error. And in order to break this exponentiation, we need to somehow break this cycle using a new form of analysis for our algorithm. And specifically, we have to remove one of the two arrows. So because the estimation error affecting coverage is basically inherent to our method of exploration, we will instead remove the dependence of the estimation error on the quality of coverage. And the key observation to make here is that the clipping used in fork is already actually doing this. And by construction, fork is an occupancy estimation algorithm that isn't impacted by poor coverage. So to see why this is the case, let me bring back the population version of the fork algorithm. Using some of the same minimizer derivation analysis we did before, you can show that the output of this procedure is the Bellman flow operator applied to the pointwise minimum, which is this wedge between two distributions, dh minus 1 pi and c times ddh minus 1. And this is a result of the clipping operator we used in the regression target to deal with coverage issues. Let me go through a visualization to give some more intuition for what this output is actually doing by comparing it with d pi, which is shown in pink. So here I'm showing dh minus 1 pi at level h minus 1, and then dh pi level h. And then the dashed lines are showing the coverage from the spanner calculated from d hat at both of these levels. So you can see there's some portions of dh minus 1 pi that aren't covered by the data. So first, what the regression objective is doing is clipping dh minus 1 pi to just the portion that's covered by the data distribution. And this is shown in teal, and it's also the inside of this output that I just displayed. And then the regression objective approximates the Bellman flow operator applied to this clip distribution, which is still covered by the marginal distribution at level h because we took uniform actions. And that's shown in the slightly darker curve at the next time step. So essentially, this output just represents the portion of dh pi that is covered by data that we can estimate. And since the occupancy is estimated iteratively, the input to the fork algo wouldn't be this dh minus 1 pi that I showed here, but actually whatever clipped version of it from the previous iteration of fork. And so to summarize all these statements, the learning target of fork is not actually dh pi, but what we call the recursively clipped occupancy, denoted here by d bar h pi. And it's basically a recursive version of the output that we defined before, where the Bellman flow operator is applied to d bar h minus 1 pi clipped to the covered portion under c times ddh minus 1. So we can show that our offline occupancy estimation guarantee is essentially that for an input clipping constant c and some data sets, fork learns to estimate d bar h pi, and the number of samples it needs to do this is shown here. So I have some proof sketch of how this is derived, but I think in the interest of time, I'll probably leave it out. I just want to highlight something that's used in the proof sketch. So the proof relies on this recursive offline estimation error bound that recursively decomposes the offline estimation error between d hat h pi and d bar h pi into a recursive term shown in yellow and the MLE estimation error shown in orange, as well as some statistical regression error shown in blue. So I'll just bring this up again later, I think, but let me just pass by it for now. So yeah, this was the guarantee that we had. And then before relating this to the proof for the online algorithm itself, I want to highlight some properties of this d bar that will become important later in the analysis. So the first is that d bar pi is never larger than d pi with equality under full coverage. So when the rewards are non-negative, this gives d bar pi some kind of pessimistic flavor because it only represents a portion of the policy's full visitation. The second is a recursive decomposition of the L1 difference between d bar pi and d pi, which expresses how much mass has been clipped away at each level. So the decomposition shows that the L1 difference at level h is upper bounded by the difference at level h minus 1 plus this term in pink, which is exactly the mass we've just clipped from d bar h minus 1 pi due to incomplete data coverage at level h minus 1, which is shown in the filled in pink mass on the left. So basically, when unrolled, this decomposition implies that the total mass that's been lost will accumulate additively over time steps. Okay, so bringing this back to our original problem of bounding the estimation error between d hat h pi and dh pi. From this, we can see that fork isn't impacted by poor coverage because it is only learning the covered portion, which is the recursively clipped occupancy d bar pi. And so in the proof, we will split the estimation error using d bar h pi into these two terms. The first is the offline estimation error between d hat h pi and d bar h pi that we have already bounded with the fork guarantee. The second term is what I'll refer to as the missingness error, and it's the not covered mass that we've clipped away, shown in this filled in green portion here. And so the key result in this proof is to show that the missingness error at level h can also be recursively decomposed as the missingness error at the previous level, plus this term shown in pink, which is the maximum offline estimation error at the previous level, taken over all policies times the rank D. So since we've already controlled this maximum offline estimation error as epsilon prime, the missingness error will pretty much accumulate linearly, or I guess 4D times epsilon prime. And so let me first go through a quick proof sketch for how this bound is derived. From the d bar h pi properties I introduced a couple of slides ago, we have this recursive decomposition where the missingness error is upper bounded by this recursive term plus this clipped mass, which is shown in this filled in area here. And if you compare this inequality and the inequality error bound, they pretty much match except for the last term. So we just need to show that this term here, which is the clipped mass at level h minus 1, is upper bounded by d times the offline estimation error at level h minus 1. So to see why this is the case, this is all based on the fact that ddh minus 1 is induced by the spanner, which is calculated from estimated occupancies. And that's again shown in the dashed line on the left. If we had d hat h pi equal to d bar h pi, so no estimation error, then by the spanner definition, we would have d bar h minus 1 pi for any policy being covered by d times this data distribution ddh minus 1 induced by the spanner. So that's shown in the dashed line on the left again. And with this perfect estimation, we have the clipped mass being equal to 0. But in general, because we don't have d hat pi being equal to d bar pi, the amount of clipped mass should be determined by the quality of regression intuitively, and that corresponds to this pink area here. Okay, so yeah, that's the proof sketch for this missingness error bound. And then before just completing the last details of this proof, I want to make a remark about how this missingness error bound is crucial for avoiding error exponentiation. So I didn't go over the proof for this, but in our offline estimation error bound, we have this recursive decomposition of the offline estimation error in terms of error in the previous time step and some statistical error. And so if you express this decomposition as a chain form with a circle representing the offline estimation error at time h, the x1 arrow reflects the multiplicative nature of the error accumulation over time steps, specifically that it's linear. So this x1 is reflecting the dependence of d hat h pi minus d bar h pi on d hat h minus 1 pi minus d bar h minus 1 pi, and doesn't include these instantaneous errors here. And we can draw a similar chain for the missingness error bound, which accumulates linearly in the first recursive term, d bar h minus 1 pi minus dh minus 1 pi, but it also includes 4d times this offline estimation error in the previous level. And so the reason why we had exponential error blowup when we tried to directly estimate d hat h pi minus dh pi without using d bar to break it up into the two sources of error is that we were essentially merging these two inductive chains and introducing these cross-hatched arrows between both sides of this graph. And basically what this is doing is having an O of D multiplication of the error over every single time step. Okay, so to finalize the proof, we just plug this missingness error bound in, and we get this dh epsilon upper bound. And this results in the online density estimation guarantee that we get, where d hat h pi is close to dh pi in the L1 norm, with the sample complexity shown here. And then to relate this back to our original problem, we now have the reward-free occupancy estimation guarantee. So we can just plug this into some zero-shot policy optimization. And this gives us the final guarantee we have for online reinforcement learning. So just some brief additional results I want to mention is that fork can be used for a standalone offline RL result. And we can also easily extend our method and results to the representation learning setting where mu is unknown. So let me briefly go over the second point first. In this representation learning setting, we assume a finite and realizable density feature class epsilon that contains the true density feature. And the algorithm is pretty much exactly the same, with some main differences being that we define the function classes differently, where they're basically linear. They can be linear in any mu prime in this density feature class. And then for the linearization step that I only touched upon before the spanner construction, we have to approximate all of our density estimates using a single feature, mu prime in epsilon. So let me just describe the offline RL result quickly as well. So the offline RL setup is that we just want to learn a policy from offline data sets without any more interaction. And in this case, the behavior policy pi d may not cover pi, so we need to clip the policy ratio additionally. I'm showing the regression objective on the bottom here, and now there are two clipping constants. There's one denoted Cx for the density ratio and one denoted Ca for the policy ratio. And so the offline RL procedure using fork is just that the user specifies some clipping parameters, Cxh and Cah for all time steps, and a reward function R. And then from time step 1 through big H, we'll just estimate d bar h pi by calling fork on the input data set with the previous estimate d hat h minus 1 pi, and then the relevant clipping parameters. And then we output, again, the policy that maximizes the estimated expected return. So this is the result for offline RL. In this case, we have to define the expected return differently. So this is j bar r pi, and that's the inner product between d bar pi and r. And the result says that with high probability, the j bar r of pi hat is within epsilon of the maximum possible j bar r. And the sample complexity involves this Cxh and Cah instead. So some comments to break down this result a little bit is that J bar R pi is a pessimistic evaluation when R is non-negative, because as we mentioned in the properties of D bar is never larger than D pi and represents only the covered portions of the occupancy. This is equivalent to the standard kind of offline RL guarantee, where you compete with the best policy covered by data, for which J bar R pi is equal to J R pi. And finally, the choice of CXH and CAH reflects a sort of binds various trade-off, where the smaller C is, the farther J bar is from J, but you suffer lower variance in your estimation. Okay, so in conclusion, Force and Fork are sample efficient RL algorithms that model occupancies using density features in low-rank MDPs. And then to properly interleave estimation and exploration in our algorithm, we had to clip to avoid coverage issues, but we also had to make some key changes in our analysis where we used d bar pi to avoid exponential error. So the main future direction that we want to go with this paper is that our current method isn't computationally efficient because we have to evaluate and store the estimated occupancies of all policies to compute the spanner, which is something we want to avoid. So that pretty much concludes what I prepared to talk about. And I can take any questions.
All right, perfect. Thank you very much. It's very cool. So, questions? All right, okay, I see that there's no questions currently in the chat. So if you have questions, then type them into the chat or raise your hand or anything like that, and then we can get to you. So I have sort of first a kind of like high-level question, which is, so this whole method is based on estimating occupancies in an L1 sense, which seems like a strictly harder problem than directly estimating the rewards, right? Because it really says that you're trying to like estimate the occupancies or the rewards, or the expected rewards rather, under every possible reward function. And isn't that like an overwhelmingly complex task? I mean, do you really think that you need to solve this in order to deal with this problem? I'm just wondering about like the thought process that led to this approach, as opposed to just estimating the rewards or the policies.
Yeah, that's a good question. So I guess I'm wondering how estimating just the rewards would work in this setting that you're imagining.
So answering Nan's questions in the online. No, sorry, no, he's having a different discussion there. No.
Oh, okay.
Disregard what I said there. So still the questions.
Yeah, so I just want to clarify what you meant by estimating R. So, I mean, does that boil down to value-based RL or?
No. So not estimating R, but estimating directly.
I get what Gergo is asking. This is my feeling as well, right? Because well, first of all, like in this setting, once you assume the access to mu, you get this like extremely powerful tools that just enables these L1 guarantees, which is like super powerful, right? But I guess what you're saying is that these seems like in some sense too good to be true, right? It's like getting distribution estimated very accurately is a very difficult task. Then what is reflected in our algorithm is that we need to use these like importance ratio, like kind of like marginalized importance sampling stuff, right? To estimate these density ratios, which is known to be difficult to work with practically. But still, like nevertheless, I think there's a very interesting step towards thinking about, instead of value functions, like what can you do with occupancies and so on. So after this project, I thought exactly along those lines, right? So one direction I haven't been able to go too far is that instead of working directly with occupancies, you may think about, for example, estimating something less demanding, like the feature embedding of occupancies, things of that sort. So I actually like started playing with a little bit, and then it turns out that in the linear case, if you write down an algorithm for estimating the feature embedding of occupancies, you actually recover basically a fitted Q. Yeah, so it's very interesting, but I think it's interesting to also think in that direction is like, we know that raw densities are difficult to work with, but is there somewhere in between, like not quite a raw density, but still maintains enough interesting properties of the densities?
So here's another thought. Maybe it's not a different thought. Maybe it's again the same as what you're describing from this different perspective. You just take all policies, or maybe like a bunch of policies, do a bunch of rollouts, right? And then use some kind of like structure of the occupancies to estimate the values of all policies simultaneously. No. I'm not making any sense here, because this approach would require you to actually run all of the policies so that you can differentiate between their occupancies somehow. Right, but still, I can't help but feel that doing all this work to have like good accuracy in an L1 sense is probably a bit too demanding. Right. Okay. So that's my question regarding like the approach at a high level, but I also wanted to understand a little bit better the guarantees that you get for the offline case.
Yeah.
Your guarantees were in terms of this, I don't remember the notation, this J bar sort of thing.
Yeah.
And
Yeah.
you said that, well, yeah, this actually says that you can compete with the best policy that is covered by the data, but what does this mean for the other policies that are not covered by the data? Does this give you like any meaningful guarantee, or?
Yeah, I mean, we can only compete with basically their value as measured on the covered portions of their occupancy. So that's what this J bar R pi is representing. It's some pessimistic valuation based on that coverage.
Right, but if you're considering a policy that was not covered properly, then what does this say? Like, do you have any sort of like way to quantify the bias that you get in this J bar? Or is it
yeah. So okay, I think
it's in the paper.
Yeah, it's in the paper, but it basically involves something like I think this missingness error. We don't have like in the case of just offline data, you can't really control this missingness error except by controlling, whatever parameters you input. So this is sort of the bias that ends up in your final guarantee.
One example that it would be nice to use is that you can think of a policy that you wish to compete with, right? And let's say this policy is actually covered, but with a pretty high density ratio. And let's say you choose a threshold that is actually lower than that, right? So you can ask, then what happens is that, the D bar for that the D bar for that policy will be less than its true D pi, but the amount that you're missing is actually can be bounded proportional to the difference in the clipping threshold, like the correct threshold that will preserve all of D pi versus the threshold you use. So in other words, this D bar pi definition is actually a Lipschitz in the clipping threshold you choose. So I guess that's it's also, I guess, related to the discussion we're having in the chat. Yeah, right. We have these like additional properties in the paper in the appendix.
So maybe that discussion can be also done live here if Alan is willing to unmute. Oh, okay, that's not gonna happen. Right, okay. So then, I don't know if that counts as a controversial question, but I guess my feeling is, or at least, yeah, what sort of like bugs me about this whole thing is like, do you guys think that it's like sort of realistic to consider these known density feature case, or do you think that some sort of like practical-ish reinforcement learning algorithms can be derived from this perspective? Because obviously, like what sells the other linear MDP setting where phi but not u is that it justifies like all of this like LSVI and these Q-learning style methods, and it fits in very well together, very naturally together with the rest of practical reinforcement learning. Like, do you see like some practical methods evolving from this line of research? We have some initial guesses as to how a practical method could be derived from this perspective.
In terms of building a practical method, I think it might be important to build this barycentric spanner that we talked about in some sort of greedy manner, so you don't, like estimate all the occupancies first. You just add things to the spanner, and hopefully in some poly d or whatever number of iterations, you get something that's approximately exploratory. In terms of like an actual RL algorithm, I'm not sure. I feel like this has some basis in those types of empirical RL algorithms where they like model something about the environment in a generative manner and then use that as as input to their RL algorithm to get lower sample complexity. So I don't know. I think that's just the vague intuition I have there.
Yeah, right. Well, I mean, I suppose this algorithm is like obviously a product of theory, right? And
Yeah, that's
sort of
true.
hard to imagine this actually being run for solving a real reinforcement learning problem. But yeah, I'm just coming from the perspective now of what would you do in this case if you were not worried about theory? Is there some obvious?
Yeah, well, I mean, like
algorithm
this importance weighting algorithm actually didn't start in theory. Like it actually started somewhere 2015-ish. There was a paper from Shai Manor's group and later a paper from Mark Bellamar, I think.
Mm-hmm.
It was derived to be the counterpart of like TD, right? For like,
Yeah.
you use TD for value estimation and you have something like this for occupancy estimation. So yeah, definitely people have tried doing something like this and get it to partially work. So I think, getting it like, work better or in what circumstances do these algorithms shine and so on. I guess it's definitely a interesting question.
Right. So again, just the speculation. So like, could you just do something simple as what you do for linear MDPs when you know phi, right? You just do a linear regression to estimate the other half, right? And then you just do you solve the resulting dynamic program with some optimism. So what happens if you do it here? Why does that obviously fail? I guess that's what I'm wondering about.
Oh. Audrey, you want to answer that?
Oh, well, why can't you solve this in a linear programming manner?
No, I think
Sorry,
what Gergo is asking is like you do dynamic programming with a linear regression.
Oh, sorry, dynamic programming.
Yeah, I think that the difference here is that the real difference is here we turn them into density ratios and have to use this linear over linear form.
Mm-hmm.
If you don't do that, actually you can show that the Bayes optimal regressor is actually wrong. Like it doesn't learn the density correctly. It has something to do with this time reverse nature of Bellman flow operator. So that's the main thing. But I mean, still regression was like it's just linear over linear functions, right? Like what's the big deal? You can just run SGD on it.
Yeah, right. But
it's
but
definitely
I guess
like a little bit more difficult than just claim like a linear regression in like LSVI and so on.
Right. So then maybe the point that I'm not getting in the first place is why do you precisely need to work with density ratios as opposed to just densities?
Okay, so I originally had slides.
Yeah,
on
it's
this,
a slide that I
but
asked Audrey to drop. But
yeah, if you have
if
you have a density here, you just there's a time reverse nature where you have basically the conditional expectation. Where is the slide on that?
Audrey, can you maybe show the calculation of the Bayes optimal predictor for this problem?
Yeah, I'm trying to get.
So Gergo, so basically what happens is that if you replace this W, W
you'll have DH
with,
minus 1 pi here in the numerator, which is just some weird pointwise multiplication of two distributions. And then on the outside, you also have like this ratio, which is the Bellman operator over DDH minus 1 dagger. And that comes from the fact that this expectation.
Audrey, I don't think we're seeing that equation you're talking about.
My bad.
It's over here.
Yeah. So instead of this WH minus 1 pi, you're going to have DH minus 1 pi. and then that's some weird like
You
pointwise
first have
replication.
the dot with two distributions, which doesn't
Yeah.
make sense in the first place.
Mhm.
And then you
Yeah.
go through it.
Yeah.
You go through p pi and then divide it by another distribution, which again, like all of this wouldn't make any sense.
Right.
Yeah. So I think some of this we already know from the marginalized importance sampling stuff, right? So that's a separate development. And I think this has been pointed out in some of those papers as well. It's like, if you want to leverage Bellman flow equation to estimate the densities, pretty much the only way we know it is to turn them into density ratios and then regression based on that. So actually in the appendix, we have an alternative way of doing this, which we suspect should also work as well, is that you can replace this regression with importance weighted MLE. So that should work, but again, you still need to do these kind of importance weighting, right? Because what you're gonna do is that, suppose you already have d pi h minus 1, then you can reweight your data with d pi h minus 1 over the data distribution, as if the earlier time step you're sampling from d pi h minus 1, right? And then you use one step correction, then it's as if you're getting reweighted samples that's looking like it's coming from d pi h. Right? And then you can just throw MLE at it. That with some modification, that should also work. We didn't figure out the details, but that's an alternative to this. But it seems like in any case, you can't completely avoid doing this density ratio between occupancy and your data distribution.
Right. Yeah. I guess the bottom line that I can see is that that estimating phi as opposed to estimating the other factor, it's a very different beast, because
it's very
not like you can use like martingale concentration or anything like that, which works for the other factor. Because there you get like real, like actual noisy transition data from which you can estimate the relevant factor.
I guess. Yeah, is there any more questions from anyone?
I guess we can cut the recording in any case.
Okay. Well, I'll stop recording then now.